Hello. Hello. Mhm. Audio. Hello. Good morning. Hello. Good morning, one and all. Okay, so welcome to one and all. Today is the second day for this system modeling. Myself, Dr. Saurabh Mitra. So today we are going to discuss the topic called as system response. This course is actually culminating to the main system modeling FDP, which will be coming shortly, again launched by GIT EC department in a couple of months. What we are trying to do here first is the tools and mathematics required for actual higher level system modeling courses. Towards that, yesterday we had done mainly 3 modules. First, we had seen different types of systems, what are the system responses. We had seen LTI system, we had seen what are the properties of LTI system, linear time invariant system, system with memory, what is system without memory. With this basic knowledge of system characteristic, we had then started linear continuous time invariant system for transform with Laplace transform. So we had analyzed different 3 different cases of continuous time linear time invariant systems using Laplace transform. There was an electrical system RLC circuit, there was a mechanical system MBK, that is mass spring dashpot. System was a temperature based system. So all the transfer functions for all the systems were seen yesterday, and their analysis were given. How to develop the model were discussed. Then we had seen how to model and how to find the transfer function for a discrete time system. So there was a difference equation. We had found out what is the transfer function for that difference equation. Finally, we had checked different intricacies for Fourier series. We had seen what is the significance of A0, A, how to find the Fourier series for an even signal. For even signal, we took a rectangular wave. How to find out Fourier series for an odd signal. For that, we took a triangular wave, which was symmetric with respect to x-axis. Finally, we had seen a exponentially decreasing kind of a wave, which was neither even nor odd. So for that last waveform, we could find that A0, An, Bn existing in that case. Today what we are going to see is there are different types of transfer function finding methodologies. It can be transfer function by using state space. It can be transfer function by using the class. Then there is another system response analysis, which is called as impulse response analysis. So among these 3, most widely used is transfer function finding of a system by classical method. So today we will be seeing 3 to 4 systems and how to find the transfer function of the system. These are the today's topics. What is exactly meant by transfer function? What are the advantages of transfer function? What are the basic characteristics of transfer? Then again, for the continuous time linear time invariant system, we will see how to find the system transfer function. Now transfer function is nothing but of Laplace transform of the response characteristic divided by Laplace transform of the input source input excitation function. For 3 systems, we will be seeing what are the transfer functions. If system is given in ODE, that is ordinary differential equation, system function is given in ODE, then how to find transfer function from that, and vice versa. So if system function is given, how to go for transfer function. If transfer function is given, how to go for ODE, system ODE. All these things we will see. Now every time I am using this word transfer function, that transfer function is nothing but very simply saying it is the gain of the system, output by input. Somebody says it efficiency if we multiply it by 100%. Sometimes it is called a sensitivity also. So in one word, whatever input we are giving, whenever output due to this input. So from input to output, this processing is done by system. So how the system is processing the input to produce output, what is the system function, this thing can be found out by analyzing the system transfer function. For 3 different systems, we will be seeing that. After we know how to find transfer function from system differential equation, we will see what are initial condition response. Response means system output. So there are mainly 2 kinds of responses we find in the combined response. So overall or combined system response is having 2 parts. One is called as zero input response and one is called as zero state response. We will see that zero input response is totally caused by the initial condition of the system, which we totally ignored in yesterday's slides. We always were saying initial condition is null. We always were saying this is a system which is initially relaxed. Capacitor we were taking, considering capacitor is not having any charge stored in it. Inductor we considered yesterday, it was not having any retentivity, it was not having any initial condition. But today, as we are going ahead, we will try to find out if initial condition and how it affects the system overall output. And that part of the combined output, overall output, is called as zero input response. And by zero state response, zero state response is nothing but the system response which is caused by forcing function or excitation function. So now on, we will not be calling input, we will be calling as forcing function or excitation function or source function. We will not be calling as output, we will be calling as response. This is more technical. Then we will see a combined system which is called as interconnected system and how to develop the transfer function model for a interconnected parameters. Now this interrelationship between system parameters we are not going to do separately. When every modeling we are doing, I will be explaining what is the relationship between mechanical system to electrical system, or maybe thermal system with electrical system, or maybe relationship between thermal system with mechanical system and all. So this is not a separate topic as the last one. It will be an ongoing thing. So for all models we are going to find interrelationship between the system parameters. As yesterday we have done for mechanical system, that mass was equivalent to inductor of the electrical circuit. Resistance of the electrical circuit was equivalent to the B dashpot. We had found that capacitance was equivalent to 1 upon spring constant. So this is called interrelationship between different system parameters. Today we will be finding what are the interrelationship between system parameters. The number of slides are less. We will be doing model slowly and very steadily. So let us start. Formally we are starting the basic. So what is system modeling? It is all about representing the physical elements or devices and their functions as mathematical equations. As of why we want to convert the whole system into mathematical equation? The answer is we are supposed to do all this simulation by using our computing facilities, and computers only understand the language of mathematics. So if you want to get a simulation done, in that case to input a specific algorithm with ambient condition, with source function, and we have to find out how the response of the system is going to be if this function is followed. So we want to make the computing facility our slave. So run a slave, we have to give this proper command is coming through the mathematical equations. So that's why mathematical formulation of a system is very much important before we want to do the simulation work. And simulation work takes us to a better system design, because whatever mistake may be there in system design, that will get rectified in process. Continuous time LTI model or CT-LTI systems are easily represented by ODE or ordinary differential. So they are most primitive kind of a system. All the classical system modeling fundamentals were developed based on continuous time LTI systems, and this is more predictable. The amount of redundancy is more in CT-LTI system randomness is less, and that's why these systems show very less amount of response error. Each of these models, as mentioned above, are having its own advantages and disadvantages, and they are also having its specific field of application. State variable model cannot be applied everywhere. So if there is a certain satisfying, then only we can apply state variable model for that kind of system modeling. So what are those conditions? That also we have to understand. It will not be discussed here, but just to tell you that every system modeling is having its own application field and set of advantages and disadvantages. Choice of the system modeling tool, either we are using MATLAB, Scilab, or there are many different kind of mathematical tools for SAS is there for statistical simulation. So choice of the system modeling tool and related mathematics depends on the process dynamics and complexity of the process to be modeled. So how many variables we are dealing with? What is the system speed? If the speed is very high and my software is very slow, in that case that tool might not be used for that specific system model. So hence depending on the system dynamics, depending on the system complexity, depending on the variables to be handled, we have to wisely and judiciously choose exactly which tool or which mathematics we are going to use. Some more basic fundamentals on system modeling. A system model might very closely follow the actual process. So that is our dream come true kind of a thing, that there is a specific system, physical system, and mathematically so correctly we have modeled it that all the responses that system is generating at every time, our simulation results also exactly same to that, or the error is very less between the simulated result and the practical result. So in that case, that model is a ideal model where amount of error is very less, negligible, or absent. But the downside is it may happen that effect, but when you are trying to fit that model by using computer and we are trying to do some analysis, it is not possible. So the model might be very correct, but it might not be easily analyzable. In that case, can we use that model for system modeling or simulation? The answer is no. On the contrary, we are finding another case that a model is very easy to analyze. It is using very simple mathematics, it is using a very simple tool. We can deal with that model very easily, but that model is not giving quite good accuracy. Two cases which you might find on the screen are contradictory. In the first case, model is very correct, but it is not easily analyzable. In the second case, very easily analyzable, but it is producing quite a lot of error. Both these cases are not proper system model. Trade-off between the system complexity and analyzability. Ideal model should be producing very less amount of error as less as possible, and at the same time we should be able to analyze it quite easily. If both these things are satisfied, then only we can go ahead with the model and we can use software or computer for further simulation to get proper amount of result. Whatever amount of error we get, maybe we have to compensate it mathematically, maybe we have to improve our design so that it might get compensated. So these first 2 points are very important. We have to keep in mind error should be less and it should be easily analyzable. Both these characteristics should be fulfilled by any system model. Third one is a further more important concern, that is the initial conditions existing with the system components play a very important role in the way response is going to shape up. If a capacitor is already holding some charge from the beginning inside it, and then we are trying to charge the capacitor by some new forcing function, in that case the response will be totally different, or the height of the voltage stored in the capacitor after the certain time will be totally different than the capacitor without any initial condition. And most of the time while doing the modeling, people do not care about what is the initial conditions, because to find how much is the initial condition existing with the system, that itself is a quite difficult job. But while doing the system modeling, we must care the initial system conditions to get accurate or exact results. We will see towards the end that combined system response is having two parts, one is called as and one is called as zero state response. Now this is very important to know that zero input response actually culminates to the transient behavior of the system, and zero state response actually goes towards the steady state response of the system. So this initial conditions or initial energy stored in the system is actually responsible for the transient or initial part of the response of any system. Hence, initial condition plays a very important role for overall system response. Finally, we come to the today's topic, what is meant by transfer function based system model. So as was told before, it is the ratio of Laplace polynomial of the response function, that is the output function, and Laplace polynomial of the input or excitation function. One loophole of this transfer function based system modeling, so what we will find is this is more of a very gross kind of a system modeling, though it is easy, but it is having a downside that it generally assumes all initial conditions to be null for ease of modeling. So this type of modeling method independent of type of input given to the system. So input, initially we are not going to consider anything like if we are giving step input, ramp input, or sinusoidal wave input, we will just consider input as an input xt. We will use input as a function xt, and we will try to find out what is the relationship between output and input yt by xt or ys by xs, system response ys for a specific type of xs. So both the statements that it generally assumes all initial conditions to be null, this also can be overridden. We will show it how we can take care of initial conditions within the system transfer function. And second thing, this type of modeling methodology is independent of type of input given. So with different types of input we can find out system response as well. So both of these things which are explained in the last two lines, it can be overridden or it can be corrected. So with this basic knowledge, we are going to go for a very primitive system modeling development for a homogeneous system. Means we are not giving any external excitation function to the system, and what response we will be finding from the system is called as natural response. So there is mainly two responses from the system. One is called as natural response for homogeneous system when no external input is connected. Second one is non-homogeneous system where we are giving some external input. So you can find on your screen at the left side that there is a water container with a pipe towards the bottom of it. So P1 and P2, it is not very clearly visible, I think. So P1 is the height of water. So there is water contained in the container, and container is having a cross section of A, capital A. So this is the so this cross section area of the container is A, you can find, and the height of water stored at some point is H. What is P1 and P2? P1 is the water pressure at the top. So as the increasing, the pressure of the water also keeps on increasing. So P2 is the bottom pressure. So P1 is P1 minus P2 is the total water pressure created by the height H, and Q is the flow rate. So this is exactly kind of a electrical system if you are trying to find the analogy. So P1 minus P2 is the pressure difference of the water, and as H is increasing, P1 minus P2 value will be increasing. There is another very important thing which is a new factor for us, which is called as hydraulic resistance. Now as there is a hole, as there is a valve towards the bottom of the container, you can see where Q is there. So this Q rate will be very high if this hydraulic resistance is less. So less is the value of R, more will be the value of Q. Exactly in the same way we are finding in the electrical circuit. So P1 minus P2 is same as V1 minus V2, which is called as a potential difference, and here it is pressure difference. In electrical circuit, R is electrical resistance. In case of hydraulic circuit, R is the hydraulic resistance. In electrical circuit, rate of charge is given by current, and in this case rate of liquid flow is given by Q. So how much water is flowing out from this container at unit time, that is given by Q. and we will find that as P1 minus P2 is more, as we find in case of electrical circuit, V1 minus V2 is more, current is more. So in case of hydraulic circuit, if P1 minus P2 is more, in that case the discharge Q will be more. In case of electrical circuit, if R is more, in that case I will be less. In case of this hydraulic circuit also, if hydraulic resistance R is more, in that case Q will be less. So this is an analogy between hydraulic circuit and electrical circuit. And what is the main variable in case of this hydraulic circuit is nothing but H. So more is the height difference between the lower and higher end of the water. More amount of or more volume of water is contained by the container, the Q value will be more or discharge will be more. Same we find in case of electrical circuit, more is the potential difference, more will be the current. So with this all basic knowledge, we are going to this whole process. But see one thing, there is no external water inlet to this container. That means there is no external output. So this is a system with natural response. So this is a homogeneous system, no external input given to the system. So let us find out what is P1 minus P2. So P1 minus P2 is nothing but R into Q. That is V1 minus V2 is equal to R into I in case of electrical circuit. In case of hydraulic circuit, P1 minus P2 is equal to R into Q. In the middle column, you can find that towards top. Now pressure difference can be modeled as rho into G into H, where rho is the density of the liquid or fluid density. It is shown in the top second column, and Q is the negative rate of flow, because the flow is decreasing, the is reducing, hence the dV dt. So dV dt is nothing but how much fluid is going out from this container, and that height is reducing means Q is a as rate of flow is decreasing, because P1 minus P2 is decreasing. So in the second line, second column, we can substitute P1 minus P2 with rho gh. G is the gravitational constant, H is the height of the water, and that is equal to R into Q is substituted with minus dV dt. V is a function of area and height. So we can find out V is equal to A into H, where A is a constant thing and H is a variable. So now we substitute in this rho gh equation V with dH, and A we have taken out, minus dV dt. V is substituted with A into H, and as A is a constant thing, we have taken it outside of the dH dt thing. So what is the change in H with respect to time? So what we find is rho gh is equal to Ra minus dH dt. But dH dt means how the height of the liquid is reducing with respect to time. Finally, the equation we find out is R into A, resistance, A is the cross section area of the container, dH dt, that is the rate of reduction of height of the liquid inside the container, rho is the fluid density, G is gravity, and H is the height. So we can find there are two terms, one is 0th order term of H and one is a first order term of H. So this is a very simple first order system and with some constants. So now as changing with respect to time, this equation of Ra dH dt plus rho gh is equal to 0. So there I have made the H as Ht, because H is a time dependent function, and we have now got the standard formula and then substituted rho g by Ra as a constant, which is called as small k. So the ODE or differential equation becomes dHt dt plus kHt is equal to 0. This equation is very easily solvable, and we will be finding that T is reducing exponentially. So if you are taking the Laplace transform in both sides, we will be finding for dH dt it is S into Hs, because we are not considering any initial condition here. That's why minus H0 is not present. So those who have done Laplace transform, they know that dHt dt will be generating two terms. One is SHS minus H0 minus. Okay, as there is no initial condition mentioned here, we are at development, but for natural response homogeneous system. Same system model, same system we are trying to see, but there is a change that you can see at the top of the left column, that there is a tap connected here. The tap is inputting water at the rate of Q1. Q1 is Q1t. So this is a kind of a unit step function. So this rate of constant liquid inlet is nothing but the forcing function in case of this second system. Hence, as there is a input function or as there is external tap present, this system is called as a forced system response, because depending on the rate of change of flow by the tap, so as we are changing Q1, we will be finding that Q2 also will be changing. So we can control the Q2 value by controlling Q1. So what our agenda is in this case, how the H will maintain itself or H will vary. So H is the output parameter, other parameters are same, that is P1 minus P2 is the height of the water, or we call it head in case of hydraulic systems. Q2 is the output response, Q1 is the rate input of liquid to the system, A is the cross sectional area, and H is the main system variable what we are supposed to control. So under this we are supposed to find out what is the ratio between H and Q1. So Hs by Q1s will be the system transfer function, and that we are. Let us see what are the system parameters. It is same as previous. So Q1 is the input flow rate. We are giving a constant flow rate. It is a step function. So Q1t is kind of a step function and it's constant. It is written. Constantly water is being inlet inside this container. Q2 is the output liquid, and H is the system variable to control. So how Q1 is controlling H? Obviously, if you are inputting Q1 at a constant rate, and we can find that Q2 that pi is very small, so what we will find is eventually H1 will keep on increasing, and after a certain time it will go to a saturation and it will stay there, it will attain a steady state. So transient steady state for this system we will see, and how exactly the waveform looks like, how the H will increase, that is nothing but the output graph that we are supposed to find out by using this overall system. H is the main variable, A is a constant, P1 minus P2 will be keeping on increasing with respect to Q1, and Q2 is a valve, so Q2 is a function of H also, that we will find. System is about H and Q1 relationship. As told before, that Hs by Q1s will be the system transfer function in Laplace domain, and from there we are supposed to find out Ht and how to plot Ht, all those things. Now let us go for detail of signal modeling, system modeling. Q1 minus Q2. So Q1 is the inlet rate of liquid, Q2 is the outlet liquid going out. So Q1 minus Q2 is how much of the stored or how much liquid the container is holding at any time is given by Q1 minus Q2. There is a concept called as hydraulic capacitance. Hydraulic capacitance is given by rho into G, where A is the cross sectional area of the container, rho is the fluid density, and G is the gravitational constant. So for electrical system we find C is equal to epsilon A by D. Epsilon is the dielectric constant, A is the cross section of the capacitor plate area, and divided by D. D is nothing but the distance between two plates of the capacitor. So in the similar line, C is a hydraulic capacitance. So hydraulic capacity divided by fluid density and gravitational constant. So how much liquid will be stored in the container at any time with the pressure difference. So whatever P we are finding in dP dt, that P is nothing but P2 at any time. So P1 is the pressure at the top or at the head of the liquid level, P2 is the liquid pressure at the bottom of the liquid level. So P1 minus V dt. So P will be similar to the voltage difference, and dt will be time, C will be capacitor, and Q1 minus Q2 will be I1 minus I2. So C is hydraulic capacitance, Pt is the change of pressure with respect to, but P1 minus P2, there is the pressure difference along H. At the outlet valve, P1 minus P2 is equal to R into Q2. So yesterday also we have seen this, that R is nothing but the hydraulic resistance of the system. If there is no resistance, in that case P1 will be equal to P2, and if P2 is equal to 0, P1 will be the cause for RQ2. So more is the high difference, more is the difference between P1 and P2, is like potential in the electrical circuit. P1 minus P2 will be equal to the flow output flow rate, which is equivalent to current multiplied by resistance. So this top equation in the right column, that is outlet valve pressure difference is equal to hydraulic resistance multiplied by flow rate, is same as V1 minus V2 is equal to R into I. This two equation Q1 minus Q2 and P1 minus P2, we can find out from there, find out what is the value of RQ2. So in that case we are finding Q2 is equal to rho GH divided by R. So rho GH is equal to RQ2 and rho GH is nothing but P1 minus P2, because H is actually causing the pressure difference between higher and lower end of the liquid. So P1 minus P2 can be substituted by rho GH, that is equal to R into Q2, and in that case what we find is Q2, that is how much is the outlet of the liquid from this container, is a function of rho GH divided by R. So less is the resistance of the hydro, more will be the outlet fluid from the system. Same as electrical circuit, less is the value of resistance, more circuit. So Q2 is equal to rho GH divided by R. So in this case rho G and R, these three are constant, and H is nothing but H is a function of time, and Q2 also is a function of time. So all those T is not shown in this equation, only we have shown Q2 is equal to rho GH divided by R. This is equal to rho GH divided by R is then substituted with the previous equation, that is Q1 minus Q2 is equal to C dP dt. Substitute Q2 is equal to rho GH divided by R. So what we find is Q1 minus rho GH divided by R is equal to C, as told before, that P is nothing but P1 minus P2. Again that P1 minus P2 is substituted with rho GH. So finally we are getting the equation as Q1 minus rho GH by R is equal to A by rho G bracket D rho GH divided by G dt. So inside D by dt we find that rho G is a constant term, so that's why this rho G can be again taken output side. So C is substituted with A by rho G, and inside P1 minus P2, which is substituted by rho, equation becomes more correct, easily understandable. We can see what is the input parameter in the bottom right equation, which is the first order forced system response. And what is the equation? It says that A is nothing but cross sectional area of the container, dHT dt, that is rate of change of height of liquid inside the container. So A is cross section area, dHT dt is rate of change of liquid height inside the rho GHT by R. Rho is the fluid density, G is the gravitational constant, HT is the time varying inside the container divided by R. R is the hydraulic resistance. More is the hydraulic resistance, less will be the value of outlet Q2. So Q1, whatever it is increasing the liquid level inside the container. So all the dynamics of this system is captured in this equation, A dHT dt plus rho GHT R is equal to Q1T. Now if you remember in previous case, as there was no forcing function, what equation we had was somewhat like this, dHT dt plus kHT is equal to 0, because there was no forcing function. In this case what we are finding is there is a forcing function, and that forcing function is nothing but Q1T. So this Q1T is helping this water level to rise and to get settled in a certain height. This height H will get to a steady state value after some time, and how to find that response, how to find that time response, again you have to take the help of Laplace transform. So this is how system model is developed. Next is how to get the system response. So system response, for that purpose we have to take this system into a different domain, and initially again we are not considering that there is an initial condition for the system. So you can find to the extreme left side of the screen, that is initial conditions are taken to be null. So initial condition happens only in case of HT. So SHS minus H0 minus. So that H0 minus thing we are considering to be null. That is initially there was no water stored in the container. So that was the initial condition, that is the basic assumption. Okay, it was an empty container initially. With that we are going forward. So again the same equation I have repeated, that is the first order forced system response is this. Now agenda is finding the transfer function. So this slide is about finding transfer function, previous slide was about finding the system model in ordinary differential equation. So how to find transfer function? Take Laplace in both sides, so dht dt becomes shs, and as was told yesterday that in time domain system is given or parameter is given in small letter, so ht, but whenever we are in the Laplace domain it is given in capital, so hs, h is capital. So ashs, the s comes because of differential part, and plus rho g divided by r, these are all constant terms, ht becomes hs. Okay, and right side the q1t becomes q1s. So q1 is the input parameter, hs is the output parameter. Whenever we are trying to find the transfer function, it will be hs divided by qs, that is output divided by input Laplace transform. That process is shown here. So hs by q1s is equal to 1 by a, from left side and right side you have to just do the cross multiplication and segregation, and we find it, and you can find that hs by q1s equation denominator, s is having a multiplicand of a, or coefficient of a. So that a we are taking at the numerator and s becomes free, and power of s is equal to 1. That signifies that this is a first order system. So dynamics of the system is very simple, very primitive, only the first order, and this is the system transfer function, that is 1 by a divided by s plus rho g divided by ar. Rho is fluid density, g is gravitational constant, a is container area which is a constant, and r is hydraulic resistance, that is also a constant. So if q1t is of unit constant rate, we are assuming that the rate at which the tank is being filled, so as there is a forced response, that means there is a forcing function or input or excitation, that forcing function we are assuming to be a step, or it's a constant unit rate of, so 1 unit of water per second, that is what we are considering the q1s. If q1t is a unit constant rate which is being inlet to the container, so for that Laplace transform of q1s 1 by s. If it is 2 unit constant rate, then q1s will be 2 by s. If it is 10 unit constant rate, Laplace transform will be 10 by s. So Laplace transform of constant is the constant divided by s. So this is very simple fundamentals we are knowing while we are doing the Laplace transform. So now what we are going to do is, in this transfer function we are going to substitute the q1s with the Laplace transform of the input. What is, we will show hs as qs multiplied by the transfer function. So transfer function is modified little bit. What we have done is, we have done rho g divided by a into r, that we have shown as a tau, a new factor. Okay, s has become 1 by a divided by s plus tau, q1s we have taken to the right side, and hs we are finding that equal to q1s multiplied divided by s plus tau. And what is q1s? q1s is nothing but the Laplace transform of unit step input. Unit step input is nothing but a constant input with amplitude 1, so its Laplace transform is 1 by s. So now hs is equal to 1 upon a divided by s plus tau. So this s has come in the denominator, separate s has come in the denominator because it is the Laplace transform of unit step q1t input to the system. What we are going to find is hs is equal to 1 upon a s into s plus tau. So we have to do fraction of this thing. So you will be finding 1 by a, if you take output side you will be finding it is 1 by tau divided by s minus 1 by tau divided by s plus tau, and Laplace transform for hs. So partial fraction first and then take Laplace transform. What we will be finding is ht is equal to 1 by a tau, so this is a constant, and 1 by a tau eventually becomes r divided by rho g. Okay, so ht is nothing but the output in time domain, that is equal to 1 by a tau 1 minus e raised to minus t by tau. It's a very simple standard Laplace inverse, and we'll be finding that ht is equal to r divided by rho g 1 minus t divided by tau. So I have substituted tau as rho g by ar, and ar has gone to the top, rho g has come to the bottom. So it has become e raised to minus tar divided by rho g. Only e raised to minus t by tau also will do. Now this is the response, and this response we have to plot for some time, and if you are plotting that over a time, maybe for 10 seconds, 50 seconds, or maybe for 2 hours, it depends on the value of tau, that how fast this blue curve, whichever is shown at the right side of your screen, bottom right side, the bottom right side blue graph is nothing but how the height of the fluid that will increase inside container if q1t constant fluid flow input is given to the system. So that's why a very faint green line you can see at the bottom, that is q1t, and q1t is nothing but a constant input. So this green line is nothing but the unit step input given to the system, and for this q1t liquid, the fluid inside the container will keep on increasing. And what is the equation for this increment? It is nothing but 1 by a tau 1 minus e raised to minus t by tau. So what we will find is initial empty, because we have taken that initial condition to be null, that means initially there is no water inside the container. Then we have started the q1t, that we have started the tap is inletting water with a constant flow, that is q1t, and fluid level inside this container is increasing and increasing at a rate, that rate can be found out from this blue line. But we have to remember that this container to overflow, because there is a outlet also in the container, which is shown at the bottom right side of the container, which is given by q2. So q1t rate is quite big, q2t rate is quite small, they will bring the liquid level to a steady state level. So in control system engineering we say the system runs away. What is meant by system running away? If there was no q2, in that case this bucket will flow, and then this bucket will overflow. In that case what we see is that h is becoming a kind of an uncontrollable parameter, the process is running away. But in this case the existence of q2 is not letting the container or bucket to get overflow. What we are finding is this bucket is getting filled up to a height of h, and that h is being sustained, and that h is a function of q1 and q2. Whereas to understand it, that never the bucket will be fulfilled if q1t is at a specific rate. Okay, so this is what is the first order forced response of the hydraulic system. Little bit explanation regarding this AT graph or input or increasing output graph is required here, because there is one system parameter for first order system which is called as time constant. So this same graph has been enlarged and same graph has been shown just to show the fundamental of time constant. Now you can see that the green line is there, the green line is a constant input flow rate which is given by q1t, that's why it is called as a step input, unit step input, and q1t is equal to 1. We have assumed if q1t is 2, then Laplace will be 2, then Laplace will be 10 by s. Here we have assumed that q1t as 1, and we are finding that height of the liquid also will be increasing. Initially it was 0, it is increasing, and then it goes and gets into saturation point. So initial part, whichever is the little bit curvy part, we can call it to be the transient region, and whenever this blue line is touching the green line, that part onward, when it has started getting saturated, that part is called as steady state part. So this blue line is actually the system response and having two parts. One is called as transient part. Transient means the initial system response part, when the system response is trying to get settled, but it is not completely settled. What is meant by settled? Settled means its value is not changing anymore. So if you see that there is a certain point towards the top of the blue graph where the blue line is touching the green line and staying along with the green line, that means the output has got saturated and height of the liquid inside the bucket or container has become a constant, and Q1 minus Q2 is constant inlet and constant outlet, and H is a constant term. Okay, so that's why it is said that by the pink line on that HT output at steady state. That means with Q1T input and Q2T outlet, the liquid level is not going anymore. What is the concept of time constant? Now, time constant is a measure of system fastness. This system, how fast it is? This blue line could be exactly following the green line if the system was very fast. So, how to find the time constant? In the equation Ht is equal to 1 minus e raised to minus t by tau, substitute t is equal to tau. It is shown in the left side towards the middle. The same equation is written at t is equal to tau. So, please look at the left side of the screen towards the middle. The same equation is written again, Ht is equal to 1 by a tau, 1 minus e raised to minus t by tau. We are trying to find out what is the amplitude of the system or what is the height of the liquid when t is equal. So, if you are substituting t is equal to tau in the output Ht equation, what we find is Ht is equal to 1 by a tau, 1 minus e raised to minus 1. 1 minus e raised to minus 1 is nothing but 0.632. Whatever is the height, maximum height of the liquid or fluid after the steady state period, what we will find is there is a time which is given by tau. You can see that after a certain time 0.632% height is achieved. So, 0.62% of its maximum height is Q1T, and after the tau time the system response is 63.2% of its maximum height. So, this is the definition of time constant. So, for faster system the tau will be towards left side, that means the tau will be more closer to the y axis. For the slower system the tau will be more far from the y axis. So, this system is not very slow, this system is not very far. So, hence for this system tau is reasonably spaced from y axis. So, for a very fast system we have to remember tau is very near to the y axis, and for very slow system tau is little far from the. So, finally towards the end it is written that at t is equal to tau Ht, there is the height of the fluid in the transient region is 0.632 times of its final output or 63.2% of maximum water height. For faster system time constant will be less, for slower system time constant will be more, and generally in control system it is seen that if time constant of a system is 5 seconds, 5 times of that. So, if time constant is 5 seconds, that means around 25 seconds time the system goes into steady state. So, it is not a anything rule, thumb rule kind of a thing. So, time constant is generally found to be 1/5 of the total settling time. So, it is a thumb rule, please remember. So, 5 tau is kind of, and for first order system we generally do not call settling time. For the first order system there is only one system design parameter, that is the time constant. Okay. So, this is the explanation response. So, how did we get the response from forced response of the hydraulic system, and how to get the transfer function. In function we have to substitute the input Laplace. So, in this case input is a unit step, we substituted q by 1 by s, we got the equation of Hs. From H inverse Laplace transform we got Ht, and in Ht we substitute t is equal to tau. So, it become 1 by a tau, 1 minus e raised to minus t by tau, and from there we found this figure of 1 minus is nothing but 0.632. So, how to test the system fastness? We should know what is the system input, we should know what is the steady state output. We have to just check in how much time the 63.2% of the steady state output of the system was reached. That is nothing but the time constant of a first order system. So, there is no time constant for a second order system. For second order system the system dynamics and system parameters are different. So, time constant is something which happens only in case of first order system. And find out the transfer function for a series RLC circuit. Why series RLC? Because series RLC is a second order system and we have already done this transfer function yesterday. So, I am assuming few things. I am assuming there is a 5 ohm resistance, there is a 1 by 6 farad capacitance, there is a 1 Henry inductance in this system. Input given is Vt. Now this Vt, so in that case we will call the current It as a step response. So It is kind of the output response and Vt is the input response. And towards the right side of the screen you might find that in this case also we are assuming initial conditions to be 0. That means there is not having any retentivity, capacitor is not having any charge stored in it. We are familiar with this equation, so this is a second order equation. I have not written the ODE in this case, directly I am processing it in Laplace domain. Is 1 into S, 1 is nothing but 1 Henry, 5 is nothing but 5 ohm, and C is nothing but 1 by 6, so 1 by C becomes 6. So Vs is equal to Is, S plus 5 plus 6 by S. Now the same thing, we are not keeping Is, we are changing current by charge. So we know that It is equal to dqt by dt. We have seen this yesterday, so Is is equal to SQS. So in this circuit, not current, but the charge is the output quantity. So input quantity is Vt, that is the quantity is the charge. So Vs is equal to SQS, S plus 5 plus 6 by S. So this is more of a proper shape of transfer function, and we are trying to find out the transfer function between input and output. So I think there is a mistake happened. In this case, this should be Qs by Vs. Okay, it is Vs by Qs, I have written by mistake. Qs by Vs, because Qs is the output and Vs is the input. Next case, what I am showing is Qs is nothing but Ys, that is the output. So equation Qs by Vs as Ys by Xs. I am having a specific reason for that, because yesterday we have seen this dynamic equation, second order ODE differential equation, d2 yt dt2 5 dy dt plus 6 yt is equal to xt. Exactly the same equation above in Qs by Vs is equal to 1 by S square plus 5s plus 6. So this is how system response is found out, system equation is found out from Laplace transform. So system equation can be given in Laplace, system equation can be given in time domain. So in this case I have shown you, if circuit is given, how to get the time domain. So please, there is a mistake, correct it. This is Vs by Qs, it should be Qs by Vs. Qs is the output parameter, in the next equation it is Ys, this is the input parameter, it is Xs. So this is how it is developed. Now we will be after this equation, that is d2 yt dt2 plus 5 dy yt is equal to xt, and this equation is a non-homogeneous equation, system equation, because the right side we are finding that forcing function which is called as xt. In this case xt is nothing but Vt. We can take this input as sinusoidal, we can take this input as step, ramp, any kind of input. Let us solve a system whichever is shown towards the end, that is d2 yt dt2 5 dy t dt 6 yt xt for output, and how to take all these things into consideration we will see, and we will find out how to solve this equation. Now what is meant by solution of a differential equation? You have to find the solution of differential equation for a specific input, that also I have mentioned. It is an exponentially decreasing input which is e raised to minus 4 ut. Now this input is a signal and this input is a causal signal, deciding ut deciding that this input is starting at t is equal to 0 and it is going towards t is equal to infinite. So ut is making the input one sided, that is the causal side of the time axis. So ut is not contributing in the magnitude, but ut is deciding the time limit input. What is meant by finding solution of the system or finding solution of the differential equation? Finding system solution means finding the time domain equation of yt for the given xt. So xt is e raised to minus 4t ut. We are supposed to find out what is going to be the yt equation in time domain, is given as given in the left side top of the screen. So this is the problem statement. One thing further has to be mentioned, what are the, so when we are solving this equation, I will tell you what is the input conditions, and with respect to that we have to find what is the solution of the system. Now the system is non-homogeneous as external or forcing function is present. What is the forcing function? forcing function is nothing but e raised to minus 4t. So this is a non-homogeneous system, and this is a second order differential equation. We are supposed to find the solution of this system. See the Laplace transform term in this equation with initial conditions. So yt becomes ys, there is no initial condition in that, but whenever there is first order and second order dynamics, in that case the initial condition effect will come. So you can see towards the top right corner dyt dt. What is dyt dt? Dyt dt is nothing but sys. Previously it is sys minus y0 minus. Okay, so this y0 minus is nothing but the initial mismatch of computer software. So d2yt dt2 is equal to s square y0 minus y dot 0 minus. So we are finding that for output there are two different input conditions that should be given to us. One is y0 minus, which will be used in the second order Laplace and first order Laplace, and y dot 0 minus. Both these things should be given, otherwise if it's not given we can take it as 0. Okay, but for proper system analysis these two things should be given to us. Whenever we are trying to find out dxt dt, what will be the Laplace of dxt dt with initial condition? It will be sxs minus x0 minus. So if we dynamic equation, three initial conditions should be given to us. One is y0 minus, for this numerical it is given as 2. Next is y dot 0 minus, which is showing as y and 0 minus in your screen. So y dot 0 minus is given as 1 for outputs. For input x0 minus is given as 0. That means there is no initial condition for the input e raised to minus 4t ut. So far I have defined the formula, so far I have told solve this. Now start solving this second order differential equation by using Laplace transform and with the help of given initial conditions. So now we have to just substitute this value. So first order system dyt dt, it becomes sys minus y0 minus, substitute y0 minus as 2. So first order dynamics becomes sys minus 2. Second order dynamics by the same way becomes s square ys minus 2s minus 1, because it is s square ys minus sy0 minus, y0 minus is nothing but 2 and y dot 0 minus is nothing but 1. So d2yt dt2 Laplace transform with initial condition becomes s square ys minus 2s minus 1. Solution of integral differential equation. So this is another application of Laplace transform, and this is another tool for system modeling. So previous equation, if you see, d square plus 5d plus 6yt is equal to d plus 1 xt. For this, if we substitute the second order Laplace transform with initial condition, first order Laplace transform with initial condition, and first order Laplace condition, system looks like this. So these are standard formulas, there is no rocket science here. So s square ys was the only term we are considering initially, but as input initial conditions are given, we have to substitute y0 minus as 2, y dot 0 minus as 1. So s square ys minus 2s minus 1 has become Laplace of d2yt dt2. In the same way, dyt dt has become sys, that is sys minus 2. 6ys, so it was 6yt in the equation, it will become 6ys. Right side, it is sxs minus x0 minus, but x0 minus is given as 0. So this big equation reduces little bit, so right side becomes sxs plus xs. Now xt is given as t, that is the input condition. We have to substitute xs in the actual Laplace equation. So left side there is nothing more to be done, it is all selection of ys parameters we will group together, and 2s minus 1 and minus 2 we will group together. But right side, instead of xs, we are supposed to substitute the Laplace of e raised to minus 4t. So e raised to minus 4t ut Laplace, with all these substitutions in the equations, what we will get is the big equation becomes s square ys minus 2s minus 1 plus 5s plus 6ys. Right side sxs becomes s by s plus 4, xs becomes 1 by s plus 4. Now coefficient of Ys are collected together and bunched together. So what we are finding in the left side, that is the output side, it is Ys s square plus 5s plus 6 minus 2s plus 11. Actually this 2s plus 11 is taken at the right side. Now this equation is very significant because Ys is having all its coefficients s square plus 5s plus 6, but they are coefficient generated from the simple Laplace transform. Now what is 2s plus 11? S plus 1 by s plus 4 we know, s plus 1 by s plus 4 is nothing but the output, the input Laplace transform. What is 2s plus 11? New thing that we are finding here, if I had not given you any initial condition, if I had mentioned all the initial conditions were 0, in that case this 2s plus 11 would have been 0. So this 2s plus 11 parameter has been generated only due to the initial condition of the given system. So depending on the given value, this 2s plus 11 thing will keep on changing. So now I'll rephrase what is this equation. So Ys is nothing but the output, so left side of the equation is the output is equal to the initial condition term plus the forcing function term. It is different, same equation I have written. So left side Ys s square plus 5s plus 6, this is the output term, is equal to 2s plus 11. 2s plus 11 is produced by all the initial conditions, and s plus 1 by s plus 4 is nothing but it has come from the input functions. So right side is a addition of initial condition terms and forcing function terms. That is what written here. So 2s plus 11 is due to initial condition, and s plus 1 by s plus 4 term is due to forcing function or external input. Now external input is exponential e raised to minus 4t. Take this s square towards the bottom, what we are finding is 2s plus 11 divided by s square plus 5s plus 6 and s plus 1 divided by s square plus 5s plus 6 plus s plus 4. Now Ys is having two terms. The first term is due to the initial condition, next term is due to the forcing functions. Why am I repeatedly saying so 10 times? Because if you are trying to find out Yt, now how can you find out Yt? Yt is nothing but found by inverse Laplace transform of Ys. So to do the inverse Laplace transform, we have to do the partial fraction first. So whatever two terms we have got for Ys, 2s plus 11 by denominator plus s plus 1 by denominator, these two terms we have to first split into partial fraction. We have got Ys. Now this Ys can be, but we will be finding there are two terms. So this Yt whatever we get will be the solution of integral differential equation, and this ut we have said because we are saying that this Yt is a causal function, that means it starts from t is equal to 0 to t is equal to infinity. So it is a unilateral Laplace transform thing we are doing, or unilateral inverse Laplace transform we are doing, which is more practical, more easily understandable, more easily explainable to students. Okay, solution is having two parts. This solution is having the first part as due to the initial conditions, whatever response we are getting for the system. So Yt is having two parts, 7 e raised to minus 2t minus 5 e raised to minus 3t. This is generated by that 2s plus 11 by s square plus 5s plus 6. This part is due to the initial condition, whatever y0 minus y dot 0 minus was given, that part has produced this 2s plus 11 by s square plus 5s plus 6 or 7 e raised to minus 2t minus 5 e raised to minus 3t part. So this part is called as zero input response. So when input is 0, what is meant by zero input response? When input is 0, that means we have not given any kind of forcing function to the system, then also the system will produce some kind of response due to its initially stored energy. So input condition is nothing but initially stored energy in the system. So this 7 e raised to minus 2t minus 3t, this response is produced by the initially stored energy in the system. It's a RLC system. So RLC system is having two energy storing element, one inductor, one capacitor. So whatever energy was stored in this inductor and capacitor, they are responsible for producing this zero input response. And if you are considering all initial conditions 0, system initially relaxed, in that case this Yt, this t minus 5 e raised to minus 3t will not be there. In that case what response you will be finding will be only due to the external forcing function, and that, on the contrary, If you see the pink part, that is the second part of yt, right side, that is minus half e raised to minus 2t plus 2 e raised to minus 3t and minus 3 by 2 e raised to minus 4t. This is having e raised to minus 4t part in it. So this clearly says that the forcing function effect on it, that's why it is 0 input response, and second part is having the forcing function in it, that's why this is called as 0 state response. What is meant by 0 state? 0 state response means we are assuming for this part minus half e raised to minus 2t plus 2 e raised to minus 3t minus 3 by 2 e raised to minus 4t, we are assuming initial condition to be 0. That means initial condition is not having any effect on the second part of yt. Combined system response is actually the addition of 0 input response, which is the first part. Now only first part we have plotted towards the bottom of the screen. You can find out that is 7 e raised to minus 2t minus 5 e raised to minus 3t. We have plotted, it is given name as 0 input response. There is a little stable part at the start from height of 2 and it has fallen and it has asymptotically touched the base somewhere around 3 or so. Okay, so this response is exponentially coming and touching the x axis. So this is the 0 input response. So whatever is the initial condition effect, that is actually inputting this much energy to the system. How can we find system energy? System energy is nothing but the area under the curve. So whatever area you are finding enclosed by y axis, x axis and this blue line is the area or is the energy contributed by the initial conditions to the system output. So yt is nothing but yt is a signal, yt plot also we will see. Yt will be having total energy under the curve, okay, and this is a bounded graph, obviously 0 input response you are finding. So bounded input, bounded output we have seen. So what is meant by bounded output? So there is a stable output, 7 e raised to minus 2t minus 5 e raised to minus 3t is a bounded output. Why bounded output? Because y axis, x axis and this graph minus 2t minus 5 e raised to minus 3t, they are producing a bounded zone, and whatever is the bounded zone, that energy is a finite energy. That's why this part, that is the part of the response due to initial condition, this will be a bounded part or this will be a stable part. Second part, which is given by the pink part of or second part of yt, this is nothing but response due to the input or response due to the external forcing function. We can see that this part a bounded energy, because e raised to initially it is not looking a bounded up to 4 seconds, but eventually it will become bounded, because you can see that e raised to minus 2t, e raised to minus 3t, e raised to minus 4t, all are bounded things. So all are exponentially decreasing, all these things eventually will come to 0. Okay, so this 0 state response also will be a bounded thing, but yes, we have plotted only up to 4 seconds, that's why it is showing that it's an unbounded energy, but eventually for this thing also will be a bounded region by y axis, x axis and the graph. Okay, so this second graph, whichever is shown towards the middle bottom, this is the 0 state response, which is called as response for input function, and first graph is response for initial conditions. And if we add these two graphs together, so that is the next part, if we add these graphs together, what we are it's coming there. So if you are adding these two things, what we will be getting is 0 input response and 0 state response together, they will be giving the combined response of the system. Okay, so combined response will be almost similar to the 0, and the combined equation also can be found out. So just wait a minute. Oh, you have to call them. So just wait a minute, this laptop response is got stuck somehow. You just correct it, rectify it, and we'll get back to you. No. It's not going to the next slide. So what we'll do is we'll bring the next slide forcefully. इसको कैसे करना है? Hello, just wait a bit, we'll get back to you. ठीक है, हेलो, ठीक है, I'll just check. Thank you. Hello, ma'am, can you just check and tell me if it is coming? Okay. No. Stream is on and this is going. So it's coming. Okay. So I'm sorry, there was some technical fault. So now we are back. So what we have found now is so this bottom there are three images which can be seen. First one is a zero input response, second one is a zero state response, and third one is the total or combined response. And we can find towards the screen what is yt, that is if you are adding the first part 7 e raised to minus 2t minus 5 e raised to minus 3t with the minus half e raised to minus 2t thing. So both this if you are adding, we are getting yt as 13 by 2 e raised to minus 2t, minus 3 raised to minus 3t, and minus 3 by 2 e raised to minus 4t. So that is the combined overall response, and ut is there to define that this system is causal. So zero input response and zero state response, if we add together, that is actually a combined response. But there is due to this dynamics, what we can find is zero input response and total combined response kind of look similar. This round things will tell you that there is a little hump you can find out in case of total combined response, which is not present in case of zero input response, and that hump is occurred because of the very fast rising peak in the zero state response. So if you are adding this zero state response and zero input response, we will be getting the combined response, and equation for that is yt is equal to 13 by 2 e raised to minus 2t minus 3 raised to minus 3t minus 3 by 2 e raised to minus 4t. So these graphs are generated by using plot command in case of MATLAB, and there are different other techniques by showing the graph. We can show the three graphs together in one plot. Three plots. The bottom one, the red one, is the zero state response. The top one, that is the little yellow one, it is a combined response, and the blue one, that is nothing but the zero input response. So zero input response is giving you the transient response which is caused by the initial conditions. Red one is giving the zero state response which is produced by the input condition, and combining this blue and red, what we are getting is the yellow one in response. So this round thing is showing the legends. So which graph is which one is very clearly seen in this plot. So all responses in one graph by using the legend function in MATLAB. Next, what we can get is the all responses in one graph separated by subplot command. So on the top you can see, so it is another function in MATLAB. We can use a subplot command. So in subplot we have to use the command as 311, 312 and 313, because we are showing the graphs as a stack, we are showing the graph as a vector kind of a thing. So it's a 3 row 1 column thing. So in 3 row 1 column means 3 1. So 3 row 1 column is 3 1, and the zero input response is positioned at 1. So zero input, which one is at the top, it is 311 position by subplot command. The zero state response which is there in the middle, it is having position of 312, and the combined response which is the YT graph, this is but the position of 313. So researchers will be using this legend function and to show the comparison between three different dynamics which may be very close, but it can be separated by different colors. And if three different responses are very different and we want to show each responses very separately, then we can use the subplot command. So with all the such examples are available in MATLAB toolboxes, you can just check. In plot command only, very simply you can find out how to program with legend, how to program with subplot command. So that was second example for today, that is while we are doing the modeling of a second order system, how do we incorporate the initial conditions and how to get the output. And we are finding that there are mainly two responses in a combined response. First one is zero input response, which is responsible for the transient part. Second one is zero state response, which is produced by the forcing function or external input of the system. So this was a new thing here. The new thing in this modeling was the initial conditions. That was a new part we have done here. Now let us go for a little bit more complex system, which is called as interconnected system, and how to model that. So after all this modeling, we now very well know that how to get the transfer function, how to get how to incorporate the initial conditions into it, and how to get the response, that is how to do the inverse Laplace transform. All those things, basic mathematical tool, quite we are doing since yesterday. So almost 5 modeling we have done, transfer functions and all these things we have found. Now let us do a little bit more complex modeling, and there is no more complex modeling than combining the systems. So these are the two systems where you can find that there is a rack and pinion arrangement. What is rack and pinion? Pinion is something, pinion and rack arrangement is actually a combination of mechanical and electrical systems. What is a mechanical system? Mechanical system here is that rack arrangement, which is shown by the green color and which is shown which is a base, okay, and on which one gear thing is moving, you can see. So whenever there is a moving part, so that gear thing is moved by a motor. So there are two systems, one is a translational systems, another is a rotary system. So why interconnected system, or why this thing is called as a combinational system? Combinational system because this is actually combining two different paradigms, one is electrical, one is mechanical. So electrical is nothing but the motor that is generating the rotating kind of a mechanical action. Mechanical action is again converted to translatory motion, and the rack thing is moved forward. So for all production chains you will be finding there is a rotary motion which is generated, and that rotary motion is like a linear slider, or there is a conveyor belt kind of a thing which is moved by the rotary motion. So it's a translatory as well as rotary motion, that's why it is called combined combinational system. It's a combination of motor electrical system with mechanical system, that's why it might be called as interconnected system. So whenever these interconnected systems are there are a lot of system modeling parameters. And finally you will see in this case a very big equation or something, we will be finding this is only a first order system, okay, but lot of things, lot of model parameters are there that if we put together, then only the finding the system model is possible for this kind of system. So we have to understand a lot of physical activities, we have to understand a lot of physical parameters in this. What are the physical parameters? Let us list one by one. So it's a combination and electrical system. Pinion is nothing but coming from the motor, it is a rotary part. It is given a torque of T in as shown in the image. So T in is the rotary torque for this motor. Theta is the angular position of the rotor at any point. Theta dot is the angular velocity of the pinion at any time, and obviously theta double dot is also there. Theta double dot is given by alpha. Alpha is nothing but angular. All these things we will be taking together in the model while doing the energy balance equation. What is rack? Rack is nothing but the translatory motion thing, it's a mechanical thing. The rack is kept on a base, or which is called as a guide. So base and rack, there are two surface, and rack is actually sliding on the base, so there will be a friction between the rack and the base. That friction is denoted by a factor capital R. All these are shown in the image, please find out. Okay, m is the mass of the rack, because this m thing will be moved forward with a velocity of v. V is nothing but x dot. Yesterday we have discussed that if you are differentiating displacement, we are getting velocity. Okay, so these are the parameters. Then there will come IP, that is the moment of inertia of the pinion. Then it is also shown in the figure, very close to that circular thing in the pinion towards the head, you can find there is IP which is given. There is a bearing arrangement, okay, and the friction already is shown. So these are, let us go forward and let us find what is there. Okay, so we get an interconnected or combined system that combines linear and rotary motion. So combined system, because this is adding fundamental from mechanical as well as electrical. Shafts with lead screws, so there is another mechanical application. Pulley, cable systems, all are interconnected system. So they all go in the same line, that there will be a rotary object that will be rotating, and translatory motion will be created from that rotary motion. Many linear actuators are of rack and pinion type. Lead screws used in lathe machines. Camshaft and follower systems are also a combination of linear motions. Cam and shaft is used in IC engines. So in IC engine also there are a lot of parts where rotary to linear, and linear motion is converted to rotary. So this is the basic understanding of rack and pinion arrangement, and we have to remember that we have to convert a rotary motion into a linear motion, and we have to do the energy balance equation, so that we are finding the system model, and system model will be first order. Same system is shown. System is having its base on the rack is kept on its base, and now input torque. So let us start from the input side. So input torque is given to the pinion system. So Tn is the input torque applied to the pinion system, and it causes the pinion rotation and angular velocity omega. Omega is equal to theta dot. In your screen you might be finding it as theta and, but that is actually theta dot. So theta is the position of the pinion, theta dot is the angular velocity of the pinion, which is given by, and theta double dot is the acceleration of the pinion, which will be given by alpha later on. Okay, so please theta dot, you read it, that theta and thing, and it is same as omega. T out. So T in is the torque given to the pinion system by the external electrical motor, and T out is the amount of torque which is transferred from the pinion to the rack system. So T out is the input, T output is the output torque for the pinion, and T in and T out, they are not same, because T in minus T out, that is the torque which is causing some acceleration of the pinion. So whatever is the torque input to the pinion, that is doing two work. One is increasing the acceleration of the pinion, and second is whatever is the torque remaining after accelerating the pinion, that is output, and that is given to the rack for motion of the rack. So that is why in the left side this blue line, T out is the torque acted by pinion on the rack. It causes the linear movement of the rack. R is the friction between the rack and the guideways. So rack is kept on the base, and between the rack and the guideways there is a friction which is called as R, mechanical friction. Rack has a mass m, and rack moves forward with a linear velocity of v. So remember, there are angular velocity theta dot, and there is linear velocity of v. So it is a rotary to linear conversion system. That is why it is called as a interconnected system or combined system. One new thing, moment of inertia. So the moment of inertia of the pinion, whatever is rotating, that is having moment of inertia here. So pinion moment of inertia IP is a function which is given by the R. Okay, so pinion is having its front radius as R. So IP and R, they are related. So we model the dynamics of the rotary input motion. Rotary input motion is coming from motor, and linear output motion. So linear output motion is obtained from rack, rotary input motion is obtained from pinion. So how this rotary input is converted to linear output motion, this is nothing but the modeling problem. So that we will model. T in minus T out, as it is explained, T in minus T out is the torque actually acting on pinion and responsible for the pinion acceleration. So T out is always less than T in, and T in minus T out is the pinion accelerating torque. It was also explained previously, that is angular position of pinion is theta, angular velocity of the pinion is theta dot, and angular acceleration of the pinion is theta double dot. So theta double dot is alpha, theta dot is omega, and theta is the angular velocity. So here omega dot is shown as omega and theta double dot is shown as theta and. So please read that as theta dot, theta double dot, omega dot, alpha, etc. Net acting torque on pinion. So the modeling starts here in the form of equation. So far we have been giving all the basic assumptions, all the dynamics so far. What we are finding is how much is the accelerating torque for the pinion. So it is T in minus T out. It is given by IP. IP is the moment of inertia of the pinion, d omega by dt. Now omega is nothing but angular velocity, d omega by dt is nothing but angular acceleration. So IP into alpha, as is mentioned here in the just previous line, angular acceleration of the pinion is IP into alpha. Alpha is nothing but d omega. So T in minus T out is IP into d omega by dt, and this angular velocity, when it is converted to linear velocity, so d omega by dt can be represented by dv by dt into 1 by r. So that r comes below this IP. So finally T in minus T out, or acceleration torque for pinion, becomes IP divided by r into dv dt. Rotation of pinion. So we know that velocity into r into angular velocity. So this is the main formula which explains the system. So rotation of the pinion results in linear velocity of the rack. So rack velocity is linear, which is given by v. Pinion velocity is circular, which is given by omega, and pinion head is having radius r. So linear velocity v is equal to radius multiplied by velocity. So v is equal to r into omega. With all these basic equations, now we will combine the rack equation with pinion equation, because rack is the input side of the energy, sorry, pinion is the input side of the energy and rack is the output side of the energy. So we have to mainly do the energy balance equation, and that will be the system model. So this is one type of system modeling which is obtained from balancing the system equations. So rack force equation, that is T output divided by R, T torque, which is coming from the pinion. So T out is nothing but output torque of the pinion divided by R. So torque is equal to force into resistance. torque divided by resistance is equal to force. So whatever is the force applied on torque applied on rack is given by T out divided by R. Okay, so T out divided by R is nothing but input force on rack minus R into V. R into V is nothing but the loss in the rack, the force loss in the rack due to friction. So first we find how much is the input force. It is input torque divided by input radius of the pinion. This is the input torque applied to the rack minus the rack friction force, that is nothing but R into V. So T out by R minus RV is the left side, that is the input given to the rack, is equal to m dV dt. Now m is the mass of the rack and that mass is going forward of V and with the acceleration of V dot. Now V dot is nothing but dV dt. So right side is the mf. So we have seen this, P is equal to mf. So total force is equal to mass into acceleration. So left side of the rack force equation is nothing but input coming from torque minus loss of force due to friction. This is the input of the rack movement. Action is nothing but m into f. F is nothing but dt. So this is a very simple physical factor, physical equations. We should understand that. Okay. Samely, if we do a little bit of calculation, we take this RV in the right side and R we multiplied with that. So what we are finding is T out. T out is nothing but the output torque from the pinion, that is equal to R into capital RV plus m dV dt. So the bottom equation is nothing but a rearrangement. Now let us see what is the pinion force equation. Already it was explained previously. Pinion torque, output pinion torque, subtraction of that is equal to moment of inertia of the pinion divided by pinion head radius multiplied by dV dt. Now dV dt is nothing but the acceleration of the rack. So you can find out that this T in minus T out, it is actually mixing the pinion parameter as well as rack parameter. Pinion is a rotating device, rack is a translatory device, a linear motion device. The pinion and rack, both these parameters are combined. So model has started converging. Now whatever T out we have found from the equation which is shown to the bottom left column, that is T out is equal to R into RV plus m dV dt. Substitute that in the equation of T out in the pinion equation. So pinion equation is T in minus T out. In this T out, substitute T out as R into RV plus m. So what we are finding is T out is substituted in this and equation has started looking little big, but this will be the maximum length of the equation because all substitutions are done. Now we have to do rearrangement. So while do rearrangement, we will take all the dV dt term to the right side and all the other terms are staying in the left side. So dV dt term is m dV dt minus, if taken to the right side, this become plus m dV dt. Right side already IP by R is there with dV dt. Okay, and one more term is there which is called as small r capital RV. So T minus small r capital RV is equal to IP by R plus MR multiply of dV dt. Next equation, what we are doing is we are doing a dV dt separate, and further what we are finding is this is the system equation for rack and pinion arrangement, but I think this is not the system equation, but anyways as given in the source, this is the equation of the rack and pinion arrangement, relationship between input and output, input torque and output velocity. So this is actually the relationship between T in and V, where T in is the input angular velocity to the pinion and V is nothing but the output linear velocity from the rack. So here dV dt and RRV, they are the output part and T in is the input part. Further separation of the things are done. So overall system equation still we will develop. There is the same equation which was shown in the previous slide towards the end. What we do is R divided by IP plus MR square. So small r is nothing but radius of the pinion, IP is moment of IP is moment of inertia of the pinion, small m is mass of the rack, small r is the radius of the pinion. All these are constant terms. So I am just mixing everything and finding a constant capital K. So now the equation becomes K T in of T. Now suddenly in the first line of this page you can see T in is only shown as T in, but what I have to do is finally I have to find out the transfer function. That means I have to convert this equation, CT equation, from time domain continuous to Laplace domain. Hence better I am showing the small t in bracket, because I want to show which one are the input parameters time dependent and which one are the time dependent output parameters. So output parameters are nothing but velocity. So in RRV, the V has become Vt now, okay, and dV dt, it has become dVt dt, okay. So in this equation now input parameters and output parameters all are time dependent, and if I am just doing separation after the constant substitution and rearrangement, the whole equation looks like dVt dt plus KRR Vt is equal to KT in of t. dVt dt, that is nothing but the rate of change of velocity, linear velocity of the rack. Left side of the equation, bottom equation I am explaining, dVt dt is nothing but the acceleration of the rack, because Vt is the velocity of the rack. Capital K is small r divided by Ip plus Mr square, all are constant terms. Again it is getting multiplied with small r. Capital R is nothing but the friction between the rack and the base, that is again a constant term, okay. And Vt is nothing but the velocity of the rack in the forward direction, which is a translatory motion. Right side also is having a bearing of that constant K, and it is connected to T in. So input parameter is T in, which is nothing but input torque to the system, and output is nothing but the linear velocity of the rack. We can see that there is no d2 Vt dt2, there is only dVt dt, that means this is a first order system, and there is only energy storing element, only one energy storing element in the system. That is why this is a first order system, and now we are trying to find out what is the transfer function. So dVt dt KRRV dt. Now what we will do is, we are not considering any input condition here. So V 0 minus, when we are taking the Laplace transform, small v 0 minus we are assuming to be 0. So dVt dt, if we are taking the Laplace transform, it will become SVS plus KR R and Vs. So there is no new term added here, only the small Vt in the second term has become capital Vs, okay. So capital K R, capital R and Vs plus KT in S. Now this will be a transfer function which will be between output and input. So output is nothing but the velocity of the rack, which is given by Vs, and input is nothing but the input torque given to the pinion system, which is nothing but T in of S. So we find that Vs by T in of S is equal to K divided by S plus K small r capital R. Small r is the radius of the pinion, capital R is the resistance or the friction between the rack and the base. So Vs by T in S is equal to K divided by S plus K into small r into capital R. Now this K into small r into capital R, it can be called as the time constant of the system. Time constant sets the fastness and slowness of the system. So more is the value of time constant, higher is the value of time constant, because we have seen the dynamics of time constant. More is the value of time constant, the system will become slower, and less is the value of time constant, the system will become faster, okay. So this is the relationship between Vs and T in S, which is nothing but the output quantity and input quantity for this mechanical and electrical arrangement, which is shown by the rack and pinion arrangement. So far we have done 3 modeling. The first modeling was for the hydraulic system, second modeling was for the RLC system, that was the electrical system, and this last modeling is for a electromechanical system. So yesterday we had done different modelings for electrical system, mechanical system, then thermal system, and later on we had done some hydraulic system part, okay. And today also we have done mechanical system, electromechanical system, electrical system and hydraulic system. So far some 6 to 7 models from different fields. It is not only electrical modeling or mechanical modeling we are doing, we have also done thermal, we have also done hydraulic, So we are actually checking the model development, model response analysis, model transfer function development from very different fields. So far what we have done today is mainly initially we had discussed about what is the transfer function and how to what are the advantages of transfer function and what are the criteria of transfer function. In the criteria we have seen that if a transfer function or if a system model is very easy to analyze but the model is full of error, that model is not chosen. On the contrary, if the model is highly accurate but the model analysis is very difficult, that system model is also not chosen. So the best criteria is a system model should be easy to analyze and it should be having error as less as possible. So that is the best system model criteria. Now there are mainly 3 to 4 different methods, classical methods of system model development. One is impulse invariance, one is impulse method, and second is the transfer function based method, and third one is state variable method. So tomorrow we will be seeing the state variable analysis and how to develop system transfer function, what are the nuances of state variable model, that we will be seeing tomorrow. That is about transfer function. Now after transfer function, a very new thing we had done today was the effect of initial conditions on system response, because yesterday's model every time we had been telling initial response is equal to 0 or initial condition is equal to 0, but we have seen in this case for the second order system model that initial conditions plays a very important role in the system response, because the initial conditions decide what is called as the transient response of the transient part of the overall system response. So if any system is having no initial condition, that means it will be having no transient responses in the system, so directly the system will try to go to the steady state. But if the system is having some initial condition, so there will happen some kind of frictional dynamics or some kind of random dynamics at the system initial responses, and after that dynamics or transient is over, then the system will think of start getting settled. So this initial conditions actually prolongs the settling time. So more is the initial condition, more is the time for the system to get settled. So we have seen this thing by using 3 graphs generated by MATLAB. One graph was for 0 input response, one graph was for 0 state response, and another graph was for the combined response. So all were done in MATLAB, and in MATLAB the same graphs are shown by 2 functions. One is by legend function, where all the graphs were shown in the same graph, in the same one graph but with different colors, and one was the subplot command, where all these 3 graphs were separately shown in a column format. So for research purpose, for thesis writing purpose, knowing the legend and knowing the subplot, both commands are very much important. And then finally we have seen the most complicated model so far. Model is not complicated from mathematical point of view, because we have seen that rack and pinion is only a first order system, so it is not very complicated for analysis, but there are a lot of parameters which are related to this rack and pinion arrangement. So pinion side there is input torque, pinion side there is theta, theta dot, theta double dot, pinion side there is IP, that is the moment of inertia of the pinion, the radius of the pinion, and all these things. In the rack side there is the velocity of translational movement V, which is same as x dot. There is a mass of the rack, there is a friction between the rack and the base. All these things are the rack side or translational side parameters. And then finally we have combined this T in minus T out, that is the rack side with pinion side force dynamics we have brought together, and after that we have found that this equation only boils down to a first order system dynamics, and then we have found out what is called as the transfer function of the overall system, which is nothing but Vs, velocity of the rack, divided by input torque given to the pinion, and which has come to be a first order system because there is only one energy storing element in the system. So this was more or less today's event, and if there is any questions and all, you can, so live chat is not functioning properly it seems, so you can send all these questions by email, or you can WhatsApp it, and if there was any issue regarding the streaming also, you can please let me know. And no questions or quizzes were uploaded yesterday, but today the quiz for session 1 and session 2 both will be uploaded at the same time, and the submission time will be told accordingly. So more time will be given to you for submission, because 2 assignments will be coming today together. Tomorrow we will be doing the state space analysis, and state space analysis, it will be done on chalk and board mode, because a lot of people having some small queries, difficulties in state space. So step by step building up of the whole fundamental will be done tomorrow. So state space analysis is tomorrow's topic, and only for GIT faculties who are having this MATLAB online ID and password. So we have arranged for a MATLAB webinar session. It will be conducted by the MATLAB company itself, core company. So today from 3 to 4 p.m. please log in to the online link with your GIT ID and password, and please attend that webinar from 3 to 4 p.m. today, which is a part of this FDP. So I'm signing off. Any questions and queries all have to be posted through Gmail, and you can ask me all the questions. Materials will be sent to you in the form of books and all, but PPTs will not be sent, because these lectures are readily available on the link which is being sent to you. So if you really need to answer your quizzes and all, please listen to the lectures once again for that portion where you are having difficulties, and answer your questions. So PPTs will not be sent. You can re-listen the session over internet on the same link which is being sent to you. So again, we'll meet tomorrow at 11 at the same time. Till then, bye for now.